In problem 6.43, we have an incline, which makes an angle theta with the horizontal. And we're pushing a block up that incline with a force, I'll just call it F. It will be pushed up to a height H, okay, like that. And that's 1 meter. And it has a mass, so we're going to try to find that. I'm going to put the normal force, the friction force that must be overcome, and then the force of gravity on this thing. And one of the questions we're asking is what is the mass that would cause this thing to be in equilibrium, because it's going to go up at constant speed, be pushed up at constant speed. And then how much work was done? Now, this is the force, and how much work was done by this force, which was provided by the person pushing on the block. I got to get my H out of the way here. All right. Now, for calculating the work, which is defined in terms of the force applied and the displacement vector through which this, and this is a constant force, is applied, that's going to be denoted as the vector R. So this force right here will have a displacement of R as it goes from the bottom to the top up here. Now, I'm going to set this equal to the x-axis and this to the y-axis so I can draw a free body diagram. And so basically, this thing's going to, that's the orientation of the axis. I probably ought to put y here so it's clear that this thing will go a distance x up the incline, okay? Now let's go ahead and get the free body diagram out of the way, because we're going to need that to calculate that mass. This is x and this is y. This is the normal force. This is the applied force, the force of friction, and then the force of gravity, which will make an angle of theta with the negative y-axis. Okay, let's see now. We're given the angle, theta is 30 degrees. The force is equal to 200 newtons. That's that applied force. And the coefficient of kinetic friction is equal to 0.18. The height to which we're going to move the block is 1 meter. What we would like to find is how much work was required to performed as we move that up the incline, and what's the mass of that block if it's going to be in equilibrium. Now the theory, well, first it's in equilibrium, so the sum of the forces in the x must be equal to 0. Sum of the forces in the y equals 0. To calculate that work, okay, that's the scalar product of the force F and the vector R. And then we're going to need to find the distance that it moved up the incline. So we're going to need the relationship between the height that the block is moved and the distance it moves up the incline, which is x. You'll find that by using the sine of the angle. There's the hypotenuse. There is the, there's the hypotenuse, and there's the vertical distance we're going to move it. So those are what we need in order to perform these calculations, okay? Let's if you excuse the pun, let's work on the work first, okay? So here's our solution. The work is equal to the scalar product. Well, I don't think I need to rewrite that. What I need to do is just interpret this right here. The work is equal to a scalar product. Well, force and R, the force and R, they both point in the same direction. They're both in the x direction. So the cosine of the angle is 1, and then I just need to put their magnitudes. That's F, and that's times x. Okay, and then all I got to do right there is put in the information I know. I know the magnitude of x, I know the height, and I know the angle. So I can plug in the numbers here. I'll leave that to you, but you just plug in the numbers into here and you'll come up with the amount of work it takes. Now the next part of the problem requires to find the mass. Now that's basically a statics problem. We've got to find the amount of mass that would set up equilibrium. And so try to work in this space without too much confusion. In this particular case, we want to establish equilibrium by finding the amount of mass that will cause that to happen. Well, we've got to satisfy equilibrium in the y direction. And if I do that, I'll take the normal force. Well, here's my free body diagram. See the normal force that has a vertical y component minus the force of gravity in the y direction. It's y component. That's got to be equal to 0. And so the normal force is equal to basically, I'll go ahead and put mg for the force of gravity. And then its y component, you take the cosine of theta to find this component right here of this force right here. So I multiply that by cosine theta. Okay. Then there's the normal force. So my force of friction then would be equal to mu times the normal force. So that'd be mu, I'll put a sub k there, mu mg and cosine theta. Okay, now I have to also satisfy the sum of the forces in the x equals 0. So I go to my free body diagram and see that I've got a positive F minus the force of friction and then minus the x component of the force of gravity. Okay, and when I sum those up, I should get 0. Well, all I have to do then is put in the force of friction here, find the component, the x component of the force of gravity. So I'm going to just solve for F. F equals to the sum of these two on the other side of the equation. Here's the force of friction. That's mu sub k times mg times cosine theta. And then I have to subtract the x component of the force of gravity, mg sine theta, like so. And all I do to find m right now, I just got to clean all this up, okay? So let's put, I've got an mg here and an mg here. So since we're solving for m, I'm going to put that on the left-hand side of the equation. mg times mu sub k cosine theta minus sine theta is equal to F. Okay. So really at this point, we can stop and let you finish this out. We know everything in here. We know all the parameters. So if you just solve this for M right here, solve for M, then you should be able to find what the mass is to establish equilibrium. That should complete this problem once you put the numbers in.